creep strain versus time curve, and we also saw strain rate versus time curve. Okay. So this is something like this, and that looks like that. Okay. So how is creep test done? Rudra, how will you obtain this?
So by loading, by constant load, after a time we measure the strain.
Yes. And how will you measure the strain? So you will have a machine which might have a dead weight, or you can have a sophisticated machine where the load is applied in a different way, and then you will have a furnace in which you will have the sample. Right? So how will you measure the extension of the sample? This is inside furnace. You can't see it. So you have to put high temperature extensometers. And those extensometers used to be a normal extensometer, still are normal extensometer, which are enhanced with a connection of ceramic rods, which can be connected at two places. And this is connected to a normal extensometer. So as these rod moves, you will get the extension recorded. Okay. This sometimes takes 10,000 hours for testing. And similar to the ductile to brittle transition region, like we have different parameters of describing dBTT. So we have FATT, FTP, NDT, dBTT, and T0. All those are defining ductile to brittle transition. Similarly, creep can be defined. So what is the parameter which you have to report? You have to report minimum creep rate or creep rate at 1000 hours or 10,000 hours or so on, or creep rate at certain value of strain. So all these things you can report. So what should be the temperature where you will be doing the test?
Sir, half of the melting temperature.
Yes. So can you name some material which can creep at room temperature?
Polymer.
Yeah. Polymer. So creep is a plastic deformation. Polymers might show elastic deformation, which is time dependent, which is called viscoelasticity. Lead is one material which can creep at room temperature. Titanium can creep at room temperature. And what about ice?
Pure.
It will not creep at room temperature, it will melt at room temperature.
Yeah.
But it will creep at lower temperature than room temperature. Okay, so how do glaciers move? They have a pressure of their own weight on it. And the lower surfaces feel that pressure, and then they start flowing without transforming to a liquid. Okay, so they are deformed. So in this case, it is going to take a long time to have significant results which you can have. And many researchers have done the testing for 10 years also. 10 years, one sample. One machine is blocked for 10 years. So when you do those kind of testing, don't use furnaces. Okay, try to get a material which can deform at room temperature, and then you do 10 years of testing because you will have power cut. Okay, and after 5 years, if the power is gone, then your 5 years are gone. But people have done it. So, so industry is not interested in this. They don't want to wait for even 2 years or 1 year, 7,000 hours, 3-4 months also they are not interested. One sample will give you one data. Okay, for statistical significance you need more data, at least 3 samples at one condition. Okay, so then you have to have more machines so that you can load more samples at the same point of time, and then just go chill, have tea and all those things, and keep coming back to your lab, and once in a while the sample will break, you will hear the sound and you will run to your lab and you will measure it, you will load another sample and you will go for tea again, or if it is lunchtime, lunch. Okay, so better to put the samples in the beginning of summer vacation. Okay. But then you don't know, you get a message that there is a power shutdown and your furnace is gone. So industry, so what can we do about it? So the qualifying criteria which industries have made now is that they want to have certain amount of strain, lower than certain amount of strain, for 1,000 hours. Sometimes they can say that for 1,000 hours at this load, if it does not fail, then we will accept the material. Okay. So in creep test, you are measuring creep versus time, and you are trying to measure all the signatures of what is happening. What can be a faster test is that to load it at higher stresses. Okay, and then you will have suppressed primary, also secondary. Because, in those testing, you are really not bothered about primary or secondary creep deformations. You basically want to know that at that stress, how much time it will take to fail. Okay. So in the similar loading, you apply more stress, and then maybe 100 hours, 200 hours, 1,000 hours maximum, and the sample will break. Okay, and then you vary the stress, and then you will get different times for the same material if you are doing the testing at different stresses, and then you plot those, and then you get something. What do you get? Something that we will see. Okay, so that faster testing is called stress rupture testing. So there are 2 types of testings you can do. One is stress rupture test, and another is creep test. And in creep test, you find out strain versus time, strain rate versus time. In stress rupture test, you note down what was the stress you have applied and what was the time of failure. Just the 2 parameters. Okay, time and the stress which you applied. Apart from that, you can do a lot of other things as well. Okay, you can look at the fracture surface, do quantitative fractography. You can measure how much it is necking, how much is the creep ductility, how much is the elongation, all those things you can do. Okay. So in stress rupture test, you are getting one parameter which is coming from experiment and one which you are applying. And then Shelby-Dawn has given a parameter which can be related with the temperature and time. So some constant into temperature. Theta is just a parameter, okay, which is relating time and temperature. If you increase the temperature, time will be lesser, failure time will be lesser, okay, and if you increase the time, temperature has to be smaller. Okay, so then you take log of these. So log theta is equal to log t minus q by some constant into t. So Q by C will be telling you the slope of the curve. Which curve? If we plot log t versus 1 by t. Okay? So on an axis, if we plot on y-axis, if we plot log t, and on this axis, if we plot 1 by t, then the slope is going to be negative, and the slope value is going to be minus q by c. Okay? So if you do the testing of the stress rupture test at different stresses, and then you plot it, sometimes you get curves. They will merge at one point on the log t value. Sometimes it will happen. Okay? Sometimes it may not happen. So these are the curves for different stresses. And for different stresses, you are changing temperature and you are getting different times and you are plotting it. Okay? So if you take log of
slope तो positive होगा ना?
हाँ, इसका slope positive.
So इधर आएगा ना y equals to
Yes. So this will go that side. So this will become C by Q log T.
नहीं sir.
क्यों?
Minus यही positive आएगा.
If I plot it like y is equal to mx plus c, like this.
Then log t is
So
equal to
what is y? Y is log t, right?
yes sir.
And then I have
Q
x
by
is
C,
q
Q
by
by C.
1 by t. So minus q by c.
Plus
Log
by
t
C.
is on this
Plus
side,
by
so that will go positive. So q by c. And then I will have 1 by t. And then what else do I have?
Log theta.
Log theta. Yeah. So it should be positive. So what I can do is I can take log t minus log theta into t will be equal to
Q by C.
right, and and so this, if the mechanism of creep is not changing, then activation energy will not be changing for that mechanism. So this should be constant. Okay, and in this case, one thing which is important here is that temperature has a weird unit. This is degrees Celsius plus 460, and the unit is represented in R. Okay, so it's just something which you should remember. So what you can do is you can write here T plus 460, and then this is equal to something called P, which is a parameter, and this parameter is Larson-Miller parameter. Okay, this is called Larson and Miller because they did it parameter and they couldn't find a common symbol like James, so they decided that we will take P for parameter and we'll symbolize it. Okay, and if you plot on x-axis, if you plot P, and on y-axis if you plot stress, then for a lot of materials you get that all the data fall on one curve. Okay, and this is also called master curve. This is a different master curve. Okay, so with this graph you can find out if you are doing the testing at two different times, and if the temperature is same, how much failure time change will occur. Okay, because P you know, so from this graph you can do that. So this becomes a design thing. You can use this graph to design your component once this graph is created for, let us say, mild steel or not mild steel, but something so Inconel, for example. And then once that is created by a research group by doing a lot of testing at different temperatures, stresses and time, then from that you can calculate that if you want to use Inconel of that grade, Inconel 700 or whichever grade you want to use, that you can use at your operational condition or not, or how much time it will take for this to fail. Okay. So this is related to the design and obtaining or predicting long-term data from the short-term curves. But sometimes this is not true. Sometimes what you predict from a short-term test. So when you are doing a test at higher stresses or at higher temperature, so some things are different when you alter the situation. When you do it at lower stresses, lower temperature, the mechanism sometimes changes for free. And therefore, the prediction for long-term data sometimes can be very, very wrong. Okay. So it is good to say that when you do it at higher stresses, at higher temperature, you are doing it for the worst scenario. But if that is not the operational scenario, suppose the testing you are doing at 600 degrees Celsius and your operational condition is 300 degrees Celsius. Okay, and from this you measure that the failure time is more than 1000 hours. So you say, fine, I will use this material. But at 300, there might be a different mechanism which is working for creep deformation, and it may happen that it will fail before 1000 hours. That also can happen. It is not necessarily the worst scenario, because you can call it worst if the mechanism is same. But if the mechanism changes, then there are some differences. Okay? So what can happen is, for example, modified 9 chrome 1 moly steel is expected to pass this qualification. So 1000 hours test, it will pass at 600 for a very high stress. But if you keep it for a longer time, okay, not necessarily it will fail before 1000 hours, but your operational conditions are such that you want to keep it for 20 years or 15 years when you make a component. Okay. So you say that at higher stresses, higher temperature, it is not breaking in 1000 hours, and then you extrapolate using that master curve, and then you see that from that master curve that if you decrease the temperature, it is going to cross 10,000 hours. Okay, but that master curve is generated from stress rupture test. Okay, it can happen that at 300 degrees Celsius, the mechanism is different and it will not cross 10,000 hours. Okay, so modified 9 chrome 1 moly can have coarsening of precipitates. So in short period of time, what you are providing is you are giving higher temperature for a short period of time. Okay, and you are applying stress. So the particles, the precipitates which are there at higher temperature, of course diffusion is going to be faster, so they will coarsen. Okay, but which one is equal cannot be said, like 600,000 hours or 310,000 hours, in which case you will have more coarsening. It may happen that for a different precipitate, 300 degrees Celsius and 1000 hours is a good environment to come out of the system. Okay, so new precipitate might be forming. So there can be a lot of things which can happen and which can alter the situation. So there have been different mechanisms which have been found. So for example, at lower stresses and at lower temperatures, it is usually seen that the mechanism is diffusion dominated, and at higher stresses it is dislocation creep. At lower stresses it is diffusion creep. And diffusion creep can be dominated by two ways. In one case, it can be that the stresses are moderately higher, temperatures are very low, so diffusion is dominant along the grain boundary, not through the grain. Okay, so when that happens, that is what I was discussing in the last class, that the maximum or the slowest phenomena will be for us atoms at the center to diffuse to the boundary, because that will be the largest distance for an atom to go to the boundary. Okay, so in this case, this is related to the grain size or grain diameter, and if the grain diameter is bigger, the rate is going to be smaller, so it is inversely proportional, and it is inversely proportional in this fashion. So you can put a constant and you can put a temperature there, and you can also put diffusivity along grain boundary. Okay, so and then you can have a different case where diffusion is happening through the grains also, and also through the grain boundary. So then it is a combination of grain boundary and diffusion through the grains, and there it is proportional to 1 by d cube, and then you can put some other constant k2 t square, and you have to put a combination of diffusivity through the grains and through grain boundary. Okay, so rate controlling step in first case is the diffusion through grain boundary, and in the second case it's a combination of diffusion through grain boundary and through the lattice. Okay, so this phenomena was first theoretically modeled and proposed by Hubel for alumina, and this is known as Hubel creep. And the second one is called Nabarro-Herring
NH.
creep.
Sir, why it's depend on the grain size, sir?
Because if the diffusion is controlled by the diffusion through grain boundary, then what is diffusing through grain boundary? Atoms.
Atoms.
And
the grain.
And so the diffusion will be slowest for which atom? Which is
Far.
farthest from the grain boundary?
Yeah.
Which atom is farthest from the grain boundary?
The grain boundary atoms.
Grain boundary atoms are farthest from grain boundary?
Center.
They are in the grain boundary, so they are not far away from the grain boundary.
Oh yeah.
So which one is furthest?
Center.
Center.
Mm.
And that distance is d by 2. So it must be related with d. Okay. Apart from these, you have, for very small stresses, you have different mechanisms. So for example, you have Harper-Dawn creep, which operates at very small stresses, and there is a frictional stress in the Norton's power law. So when we write epsilon dot is equal to some constant into sigma to the power n, so this is basically for secondary stage creep. This is also known as power law creep. Okay. So this power law creep is valid here because strain rate there is not a function of time. Okay. So, and what is happening in the secondary stage is the strain hardening is getting compensated by recovery. Okay. So it's a steady state situation, and that's why it is called steady state creep rate. Okay, it's a steady state between recovery and strain hardening. So in many metallic materials, when you do the testing, conventional creep testing, and then you capture the secondary state, and there you find out the creep rate. Okay, and that you have to do at different stress levels. You have to perform the testing at different stress levels. You have to find out the values of steady state creep rate, and then you plot those on log curve, and then the slope will be the coefficient of this equation, the exponent of this equation, and from the intercept you can calculate the coefficient of the equation, right? So so many times what is done is that you do the testing, and you really, so when you plot strain rate versus time, you really don't see anything. So you see something like this. So in this case, which one will you take as a steady state creep rate?
Bottommost portion. Bottommost portion.
Bottommost. Rudra, physicist. Bolo, best student. Which one you will take? बोलो बोलो।
बॉटम तो नहीं आएगी,
बॉटम तो नहीं आएगी, करेक्ट।
कुछ रेंज आएगी इसमें, क्योंकि हर
कैसी
बार
range?
बॉटम सेम नहीं रहेगा।
हर बार? कौन सी बार?
मतलब जितनी बार टेस्ट करेंगे हम,
ये तो एक ही कर्व के बारे में बात करता है।
मतलब
We will have to generate this kind of curve for different stresses, okay? And for each curve we will get one value of epsilon dot ss. तो वो epsilon dot ss इस कर्व के लिए कौन सी वैल्यू होगी?